Good morning. So I wanted to check your attendance today. 이재혁 씨, 고하늘 씨, 심준호 씨, 이승빈 씨, 이정태 씨. If you are here, then please leave your message. 네, 고하늘 씨, 안녕하세요. 심준호 씨, 안녕하세요. 이승빈 씨, 안녕하세요. 이재혁 씨, 안녕하세요. 네, 이정태 씨, 안녕하세요. Okay, let's go to the next page. 이충하 씨, 정상아 씨, 그리고 홍주표 씨. 네, 이충하 씨, 정상아 씨, 그 다음에 홍주표 씨. 다 오셨군요. Okay, let's go to the third page. 김민선 씨, 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨. 네, 배서령 씨 늦지 않으셨고요. 예, 김유신 씨, 김민선 씨, 배민열 씨, 네, 서하연 씨 다 오셨네요. Okay, now we move to the last page. 조대현 씨, 최승규 씨, 김성수 씨, and Mr. 나단 마니큐에르. Okay, good morning. 네, 조대현 씨, 김성수 씨, 최승규 씨. Okay, okay, I think that every enrolled student has come here. Okay, then let's start today's lecture. How was your homework number 4? It has two problems, and yes, some students ask me questions, so it is really encourages to ask me questions through email. So I'm happily will happily in response to your questions. Okay, so well, before starting today's lecture, so I wanted to discuss about our homework number problem 2. So because there was some email questions, so as before, we will introduce a certain sinusoidal excitation. So say, for example, if this one is a sine amp and sine omega V amp sine omega t. Then here it was, for example, well, if we are working at 1 hertz, then that will become just 2 5. Oh, sorry. That will become just 2 5. And if we are working 1 megahertz corresponding to 10 to the 6 hertz, then omega will be 2 pi multiplied by 10 to the 6. You know it. And yes, in this case, we can introduce a certain circuit element, a nonlinear circuit element, which is not very clear to us. How can we fabricate it? But let's say now we have this kind of configuration. And the one in our homework number 4 and problem 2 is given by just to behave like it behaves like a resistor when the applied voltage is larger than V1, if I remember correctly. So previously or before applying the voltage larger than V1, then this nonlinear element can be considered as just a disconnected one. So as a time function, our voltage source, so the voltage across here ground, and let's just say that this is in node, then in node voltage of the in node can be written or drawn as anyway, can be written as in this way. And you know that this peak value is corresponding to what? Corresponding to our amplitude. And of course, for the lowest one can be corresponding to minus V amp. You know it. And if you have any question, even during my explanation, please interrupt me anytime. And starting from 0, we will have the first period here. And of course, this first period time t is given by 1 over f, inverse of our frequency. And frequency is given by, so we have a relation between angular frequency and frequency, like angular frequency is just a scaled version of our frequency. So we will have 2 pi over f. So now we will have this purely sinusoidal one. However, if the voltage of in node, in node means that here is larger than V on, then there will be no output voltage. So output voltage means that I will just take this node voltage as an output voltage. Then what will happen? Let's just say that happen to be this is the value of V on. Then if we draw our output voltage as a function of time, then up to this point where our in node voltage is larger or smaller than our V on, then we will have something like this. So can you see it clearly? Okay. So we will have just 0, 4, this guy. So up to now, are you guys with me? So if you have any questions, my explanation up to now, then please let me know. So now think about the situation where we are around this time instance. The voltage is very close to V on. So in this case, let's say that our voltage is quite close to V on. Then what will happen? If our input voltage is close to V on, then still our nonlinear element does not conduct. So it says that, oh, since voltage is so small, it does not overcome my threshold or my own criterion. So I will not allow any current. So since the current is 0, so obviously this resistor current should be 0. In order to have resistor current 0, we have to apply 0 voltage to the resistor. Then what happens to our nonlinear element? In this case, okay, all of our input node voltage is applied to our how can I say nonlinear element. But now think about the case like V on voltage is now given by V in node voltage is given by the sum of V on and a slight positive number. Oh, although not that high, but let's assume that now our input voltage is slightly overcomes the V on criterion. So now we have an excessive voltage, additional voltage to turn on our nonlinear element. So then what will happen? Up to V on, everything is just consumed by our nonlinear element. However, now for this excessive voltage application, then now the behavior just changed into what? Changed into that of two serially connected resistors. So I mean that in this case we can imagine like this. Here we have R, and here we have the equivalent resistance like 1 over Z. Then yes, now we will have here we have out node, and you know that in this discussion we should not consider this V on, because V on was just used to make this configuration. So V on is just spent to turn on our nonlinear element. Only the additionally applied the voltage V can be divided by this serially connected 1 over Z and 1 over Z and R. Of course, the voltage splitting ratio will be just 1 over Z plus R, and here we have R. That will be the voltage division ratio. So we will have just here this value as an output node voltage. So let's come back to our original problem. For example, if happen to be if one of z is equal to r, then what we will have for this part is now we have here certain excessive voltage and its peak value will be just given by V amp minus V on. And when we happen to be have the equal or same amount of our equivalent resistances, then we will have just divided by half. So we will have just half of it, you know. So now this one is given by half of V amp minus V on. Of course, this is corresponding to the case where when 1 over z equal to r. If we have, for example, much larger or higher resistance than r, then obviously we will follow that one. We will follow almost close to 1. So if r goes to infinity, then we will have the ratio quite close to 1. Or another case is if g goes to 0, then again this ratio will be 1. So anyway, let's come back to case where we have comparable equivalent resistances, then we will have just half of it. So that will be the answer for our second problem. Okay, of course, I do not expect everybody answers just like this way. You have your own freedom to set your parameters. So yes, if that sounds reasonable, then our TA, Mr. Kwang Lee, will give you some reasonable credit to you. So don't worry about your answer is not perfectly to match mine shown here. But anyway, it is quite clear that if we have, for example, very I mean that I have to say that this is not this I made a mistakes here. G equal to 0, that doesn't make it, because if we have G approach to 0, then this part will become very large, so we will have just vanishing values. So in order to have still value 1, then we have to have also infinitely large G for 1. Sorry about that. So let's come back to our nonlinear device once again. So now we understand the output of this AC to DC converter really depends on two factors. Like I will just draw the magnified version of this time varying signal once again. Yes, this is time t, and the output of our circuit here is determined by yes, this is the one for our, how can I say, useful and non-zero signal. For this range, and this range, our circuit will not conduct and will not give us the positive value. So if we have a large V on, and think about another case like we have much lower V on. So say V on is much lower. Then what will happen? Okay, in this case we can expand the time duration for positive signal output signal, and more importantly the output signal we have is determined by the amplitude of our output signal is given by what? The difference between the amplitude and V on. If we have a much lower V on, then what will happen to our output signal? Then now we will have V amp is given, but if we adopt a nonlinear device which has much lower V on, then obviously we have much larger headroom for our voltage variation. For example, if we just adopt this R on, high R on, then our output will look like this. And if we apply the V on, very low value, then we will have a larger one. So which one is preferred? How about your opinion? So if we have two different curves, like from the same input curve, black one, by changing your nonlinear element, you can have two different output signals. One is red colored and one is blue colored. And if your intention is to get maximum DC component out of it, then obviously your choice will be what? So could you please answer or show your opinion, every student? So blue and red, there are two curves and we want to maximize the DC component. So what should be your choice? Please. Thank you. Thank you for your feedback. How about other students? So I'm asking to all our students. So please respond. Yes. Thank you. Okay. So yes. Thank you for your feedback. Oh, oh. So, oh, yes. So you are quite right. Thank you. You are quite right. So I made a mistake. No, thank you for your uh, really nice comment. So that is great. So since we have wider width for our output signal, my drawing should be yes. It is quite good to have such a good comment on my mistakes. Okay, thank you. Yes, thank you. And now, as 이충아 씨 correctly pointed out, our output signal red colored one should be widened because even the voltage range where our nonlinear element conduct becomes wider, and that will be the correct description or correct schematic drawing for our red colored one. And if we consider certain average values for this blue colored one, yes, there will be somewhere here. And if we consider the average, DC average of our red colored one, that will have a much higher value. So, as all of you correctly answered, the answer is we prefer to have red curve when we try to maximize the DC output. So, simply speaking, how can you obtain this kind of a red colored one? What was the difference between blue curve and red curve? It has a small V on value. So when V on is close to 0 volt, then yes, we will have a more efficient conversion from AC to DC. And if we have a larger V on value, then in order to just turn on our nonlinear element, we have to spend most of our applied voltage, so that introduces inefficiency. So if our application is really related with this efficient conversion, then maybe this small V on voltage will be quite a desirable quantity. Okay, so then let's think about this one. Yes, now think about the IV characteristics of our nonlinear element once again. Then how does it look like? Yes, here we have a voltage where this circuit element really turns on. Now say this is V on, and if we draw our schematic, then yes and yes, that was assumed one. And now we understand, in order to have a better performance, our V1 is approaching to this y-axis. I see. And another parameter we have to consider is the slope. Slope is given by just z. So if we have larger conductance G, then we will have U. And if we have really small conductors, then we will have also certain differences. What happened? If you remember correctly, if the additional voltage was written as delta, then the ratio was, so input to output conversion ratio was given by 1 over G plus R, and here R. In order to have this ratio close to 1, we have two choices. For example, relatively large R or relatively small 1 over Z. So in order to, let's say that this R is just given as a certain constraint, then now let's say that we have only one knob or 1 degree of freedom um, for our designing. So we can just change the values, conductance values, then see what happens. In order to make our ratio close to 1, then obviously we should increase our conductance value. Then, mm, then now come back to our graphs. So this is small and this is large. What is your choice for efficient conversion? Obviously, you can now understand if we have a larger and larger G value, then that will just copy and paste from input voltage to output voltage. So if we collect all of information, then now we understand the most desirable IV characteristics for this circuit. So if we are allowed to make a real ideal graph, then I wanted to suggest that the ideal one is like this. So everybody, are you with me? It means that the V1 is really close to 0 and the conductance G is really close to infinity. So our IV characteristics just looks like almost a vertical line. That will be best for our conversion. So if we adopt this kind of really ideal one, then what will happen? In this case, then our curve once again just look like this. Oh, yes. So the positive phase of our input signal is just copied into the output one, and the negative phase of our input signal is completely blocked and it is not transferred to our output voltage. So that will be the ideal, most desirable behavior of our AC to DC converter. However, you can really easily understand that is really an ideal case, and in reality, maybe we will have a certain V1 value, and also we will have a certain slopes, non-negligible slope here, so corresponding to moderate value of Z. So that will degrade our output voltage from the viewpoint of maximizing the DC output. So I wanted to ask everybody in this classroom to type whether you have a question or not. So if you have understood all of my discussion up to now, then please leave the message like I have no further question, like that. And if you have any question related with this problem number 2, then please let me know. Okay. Thank you for your feedback. Okay, thank you. Oh, um, 이정태 씨, thank you for your question. Thank you. That is really good question. Uh, according to him, so his question was, how can we decide V on value? Actually, so think about V on. Now we can consider three different components in this circuit. Yes, now we have three different components. One is voltage source and one is load resistor, and here we have a nonlinear element. Then what is so V on is a property of what? So V on is property of this nonlinear circuit element. So if you really wanted to change your V on value, then you have to select the appropriate nonlinear element. So if you visit your part shop, then you can find many different, different circuit elements which behaves similarly, however with different V on values, and you have to select the one which is quite suitable for your application. So it was a really good question, and in when a circuit is really fabricated, it is not possible to change V on. So it is the, how can I say, the role of designer. Designer should select proper circuit element to make our circuit performs better. Okay. Okay, thank you. And okay, so I'm once again asking all of our students. So we have more or less 18 students in this class, in this lecture, but only around 10 students left the message. So I'm still waiting. All of you give me feedback. So, so up to now, we have thought about a certain element, certain non-linear element, which acts like a resistor, which conduct current, and which acts like just insulator, which does not conduct when it is biased in positive way or negative way, respectively. So now we are curious, how can we build such a thing? Now we understand, yes, if we can have such a thing, oh, when it is biased 0 or close to 0, or biased 0 or larger than 0 or larger than V on, yes, it conduct. And when it is biased in negative way, or yes, biased smaller voltage than certain V on value, it does not conduct. So if we have such an element, yes, that will be quite good for our application. But our natural question is, okay, then how can we fabricate it with our semiconductor technology. That will be the, the topic of today's lecture. Today, I will talk about how can you really fabricate the certain thing. Okay, so if you have any question during my lecture, then please interrupt me. You can leave your question in the chatting log, then I can immediately answer your question. So now let's remember, try to remember our previous lecture. At the end of our previous lecture, I just draw a schematic of a silicon wafer. And as I told you before, the typical thickness of our silicon wafer is just around 600 micrometer, and 600 micrometer is just 0.6 millimeter, and yes, that is 0.06 centimeter, so that is really thin. And you know that if we try to build a two-terminal device or two-terminal circuit element, then actually we have to provide two terminal. Yes, otherwise we don't have terminal. So typical way to provide a terminal to this system is, yes, we introduce certain metal and separated another metal. Then we can have one metal and one metal here. Of course, this is silicon and this is good metal. Then, of course, since this is yes, 600 micrometer scale, but please note that my drawing is not perfectly scaled. Some part is enlarged and some part is just drawn in a short length scale, just in order to give you certain feeling about the importance of each part. And let's just say that now this one and this one is connected to even wider part. Yes, so this is just a millimeter scale, so we have to have a really wide one, and that larger part is actually connected to external world. So when we just pick up a certain circuit element, and when we have a look at them, if we just buy a discrete part from the part shop, then usually it has certain metal lines, so as a terminal. Yes, yes, for example, this one, each of them is designated as a certain name and it has its own role. However, internally, it's like this. Small leg of our chip here is corresponding to, in this scale, in our scale, it is corresponding to very large and wide metal line. So that is just regarded as really a good conductor. So we will not consider any kind of voltage drop across that metal. So now our focus is on here and here, the small part, the central important part of our chip. Okay, so up to now I think that is quite acceptable to you. So now we have to think about the internal structure in this chip. So our aim is to provide certain nonlinear behavior into this system. So where should we implement such kind of nonlinear property? For example, if we try to make it here, Usually that is not the case. So here we have 6 micrometer thick scale, and this one is still just a micrometer scale. So although I have a little like almost laterally wider uh, thing, but in reality it just looks like this. This is very thick, and they are just fabricated each other. So this is the real scale for this one. So if we try to make it here, it is not very efficient. For example, if we try to get the current conduction between this left electrode and right electrode, then if this is really the central part of current conduction, then we will have this kind of current conduction path. That is not that much efficient. So typically in the semiconductor industry, what we do is just to try to implement an important part here, just close to the top surface of our silicon material. So top means that maybe you can think that now we use 50-50, so the lower 50% is just not used, and we are now using upper part. No, it's not. So in reality, we just utilize just a few micrometer, really a few micrometer on close to the top surface that is used for our device fabrication. Oh, then what is the role of this part? Of course, the role of this part is just supporting material. One, the supporting material for this system. Also, another one is the sink for heat. Heat sink. So you generate a certain heat when you apply the voltage, then by action of your device operation, then frequently we have the heat generated. Then that is this substrate is frequently used as a way to dissipate the generated heat to the outside. Okay, so usually we are quite much interested with what? Interested with really a narrow surface region close to the top surface. Yes, this is top surface, and we are more or less interested with this region. Okay, so then now think about this one. Instead of such kind of nonlinear element, first we wanted to build a register. This one is a linear element. However, anyhow, we have to be able to make it. Then how can you make a simple register to this silicon wafer? So the way we do is introduce certain area where the resistivity of our silicon wafer is intentionally modulated or controlled. I mean that, let's say that here we have introduced a certain region which is well separated from the other part by its electrical property. So usually what we have to do is like this. Usually this silicon wafer is really highly resistive, and in this part of so therefore if we just try to build a resistor with this substrate itself, then it is not in a range of our interest. So usually when you say a resistor, you are not talking about, for example, giga ohm or tera ohm like that. So you just wanted to introduce several mega ohm or even smaller like a kilo ohm or several ohm. So in this case, silicon wafer itself, without any treatment, it becomes too highly resistive. So in order to make a more reasonable value suitable for our application, we introduce a certain part, certain region, which is less resistive. It sounds a little bit more weird because we are now trying to make a resistor, but we have to introduce less resistive region for our system. But that's true. So silicon wafer itself, usually called as a substrate, this region is too highly resistive. So it is not good for our application. So what we do is intentionally fabricate the part whose resistivity is much higher than, oh sorry, whose conductivity is much higher than this substrate region. Then in terms of resistivity, then okay, that is quite acceptable to our purpose. So we can control the resistivity of that part. Okay. So then your natural question will be, then how can we control the resistivity of this region? So what is the difference between this part and this part? Yes. So anyway, I'm trying to postpone some technical discussion as much as possible. So since this course is really introductory, so I wanted to make it in a plain English as much as possible. So if you have any question up to now, then please let me know so I can explain more about this general description. Of course, later on we will discuss more qualitative or quantitative description later on. But if do you have any question on my description up to now? So one thing we have to keep in mind is basically silicon wafer itself is really highly resistive, so it is not very good for our chip fabrication purpose. So what we do is always make even less resistive part. For example, this one is this part is less resistive than this part, and also we can introduce further sub region like this and that. oh, this part is even less resistive, and this becomes even less resistive. Oh, we can try many different sub-regions, of course close to the top, even closer to the top part, top surface, and less resistive. So this is a usual way of fabricating our device. Then in terms of electrical conductivity, how does it look like? So from the viewpoint of conductivity, then this part is really avoided. This is highly resistive, so I don't want to pass through the current, or does not pass through this region. So starting from certain one metal part, so this is good for its conduction because this is most less resistive. So after that, it just pass through this less resistive part, and it does not go to this way. Yeah. So after that, it meets the most less resistive part and least resistive part, and it goes away in this way. So that is the typical way we make a resistor. Then then maybe you can ask me question once again. Okay, then this less resistive part is good enough to make a resistor, but why do you introduce another part close to our metal line? Here, yes, it is quite acceptable. However, if so, but in my presentation, I just introduce once again even less resistive part. This one is the least resistive, so among three. So what is the role of this really highly conductive part? So do you have any idea about the role of this one? The role of this part, so highly uh, conductive part, is the bridge between this metal and semiconductor part. So if we introduce really less of, so just moderately resistive part to metal, then this metal is good for current conduction, but if how can I say, let me just magnify this part a little bit. Yes, let me just magnify and draw it once again. We can say here we have metal, and now we have semiconductor, silicon. And if this part is not enoughly conductive, then the meeting point here, or interface between metal and silicon, will show certain non-linear behavior. Yes, so since our purpose is to invent or fabricate a nonlinear element, that sounds quite reasonable and desirable. However, please note that what we wanted to do in this class is not introduce a certain non-linearity to this metal semiconductor interface. That should be just to work as perfect bridge between just metal and connected to the external world and semiconductor world. So in this case, it is not a desirable one. So what we wanted to have is just interesting thing should appear in this part. We wanted to control the current conduction in this way. We wanted to focus that part. So controlling that small part, we wanted to control the overall electrical property of our circuit element. So that's the reason why the part or region really close to our metal here is usually made as a highly conductive part. Yes, say that yes, this part is really highly conductive. Of course, when I say highly conductive, it means that this is really contrast to our highly resistive part. This is really less resistive part. Okay, then now if you understand all of this, then now concentrate on this part. So we are now focus on only this part. Why we can allow just to concentrate on this part? The circuit element itself has so many internal structure. For example, let me just name them. This guy. Yes, it has a substrate. However, since that is really highly resistive, so there will be no current for this highly resistive line. So that is eliminated from our discussion. And the metal line connecting external world and our internal metal, since that is really large and so highly conductive, so there will be no voltage drop across this metal line. So we just neglect it. And same for this guy. And also we can think about the interface between our metal and semiconductor, metal and silicon. But usually the semiconductor part directly attached to the metal is really well designed and close to the metal, the property. So we do not expect any voltage or significant voltage drop across this interface line. So that is none of our concern. And how about this guy? Now, this guy, the highly conductive region itself is so highly conductive. So there will be no voltage drop once again. So simply speaking, I can say that the part related with the current conductions, this guy, this guy, this guy, and this guy, and this guy, are so much highly conductive. So no voltage drop occurs. So they can be safely neglected from our discussion. Also, on the other hand, the part which does not contribute to the current conduction is also so much highly resistive. There is no chance 4 electron current flow through this region. So now we can consider only the remaining part. Yes, we can now consider only this part. Depending on the electrical property of this purple colored box here, now we can control the overall electric property. Okay, if this one is not so much conductive, then overall system, overall circuit elements will not conduct very much. On the other hand, if this purple box becomes really highly conductive, then our entire circuit element will conduct quite easily and powerfully. So that is the way of approach. Okay, so our system, our circuit element has really many internal structures. However, either highly conductive or either highly resistive, so they can be just neglected from our discussion. And now we can just concentrate on this central part. So that was my discussion on this overall structure. Do you guys have any question on my explanation? So now please let me know whenever you have a question. And even when the session is over, you are quite much encouraged to send me on email communication. So I will be very happy to receive your question and answer to your question. Not directly related to the homework problem, but any question related with our lecture will be really welcome. Okay, then so now we have to consider the way to control the conductivity of that central part. That is now our main discussion. So as I told you before, when in its intrinsic status, so like this substrate, usually the silicon is so much highly resistive. So it is quite resistive. But when I say just qualitatively resistive, what is the role of, what is the reason of this high resistivity? So it is quite much related with lack of charge carriers. So when I say the substrate is highly resistive, it means that there is in this substrate region there is almost no charge carriers, which allows the current conduction. So think about this one. There is one city and there is another city, and there are so many persons here, and there are so many persons here. They are willing to communicate between two cities. However, unfortunately, by certain reason, no transportation is allowed between two cities. For example, every day, just one small bus is allowed for one way and return path. That is allowed. Then let's say that there is 1 million persons here and 1 million persons here. However, if it can takes just 40 passengers, then how many exchange of a person can be allowed between two cities? So obviously per day, for a single day, we can have at most 80 persons can be exchanged between two cities. So think about this one. Quite similarly, we have here, we have also here, we have two regions, so spatial regions, and many electrons are there, and there is also many electrons are there. However, let's say that there is no way to move these electrons. So then what will happen? Although at two endpoints we have many electrons, but if there is no way to move them, then the current conduction will be really minimized. So quite similarly, when we have the certain part is highly resistive, it is directly connected to the lack of charge carriers. So simply speaking, I wanted to say in this part we have almost no electrons which can contribute to the current conduction. Of course, you can ask me in this way. You know, silicon has the atomic number of 14. Its atomic number is 14, and it means that each silicon atomic core has surrounding 14 electrons around it. So we have so many electrons, so 14 times more than number of silicon atomic core. And usually the number of silicon atomic core is orders of 10 to the 22 per cubic centimeter. So if we consider a silicon chunk which has, yes, this is 1 centimeter and 1 centimeter and 1 centimeter. If we have such a small cube, then inside it, the number of silicon atomic core is orders of 10 to the 22. And when we have 10 to the 22, then number of electrons inside that system will be even 14 times larger than that. Oh, we have plenty of electrons in it. However, when we say electrons in this part, we do not count all of these electrons inside our system. So we will continue our discussion in the next lecture. However, when we say electrons in this course, so it has some special meaning. So that will be discussed later, so in the next lecture. But I'm quite happy to discuss about the realistic structures or the realistic realistic structure of a semiconductor chip. So usually when we talk about something in this course, we only think about this part. However, before discussing about this part, we have to understand it is in physical size, it is a really small one. This part is physically very uh, thin and narrow one. However, since all other parts are highly conductive or highly resistive, so their contribution can be neglected or fully counted. So that's the reason why the only important part we have to keep in mind is this part. So controlling the electrical property of this box part, we will have the control over the electrical property of entire circuit elements. Okay, so since the time is up, so if you have any question, then please send me an email, then I will happily respond to all of you. Okay, thank you for your participation today, and I have two things to say, tell you, so quite quickly. Still, you have homework number 5. It will be posted in a short time. So one is, and as I told you before, we will switch to the in-person lecture when the university regulation allows us. So I don't know whether that will realized or not, but whenever it is allowed to have the in-person lecture, then we will switch to the in-person lecture. Okay, that is my announcement. And okay, thank you for your active participation, and see you next Monday. Bye.